Hello, you're welcome. All right, so now we have another topic we're going to be discussing, and this is current electricity. Okay, so now remember when we treated static electricity, okay, we said that electricity is being divided into two, okay? One is static electricity, which of course is electricity due to static or stationary charges. Then the other is current electricity, which is electricity due to a mobile charge. Okay, so now we're gonna be looking at current electricity in this tutorial. So let's start with the definition. All right, now current electricity is a type of electricity that is generated by continuous flow of electronic charge, of course, electronic charge, okay, through a conductor, okay, which is driven by electric cell. So when there's a continuous flow, okay, excuse me, when there's a continuous flow of charge, let's say this is a conductor, all right. So now, anytime you supply um potential difference in this conductor, what happens? Okay, current flows by actually moving charge from one part. Let's say this part of the conductor is A and the other part is B. Okay, so the electron is being generated from the cell, and it being moved from one part of the conductor to the other, right? So that is current electricity, continuous flow of electronic charge. Okay, so please take note of that. So we're going to be looking at electric current. Okay, so we'll talk about electric current. So just okay, here we go. All right, so now what is electric current? Please pardon me. What is electric current? That's what we're going to be talking about now, right? So I hope you're with me. Okay, so now electric current. Now electric current is defined as the rate of flow of electric charge, okay, um, in a conductor. Or this is one way of defining it, okay, or you can define it as the quantity, okay, electric current as the quantity of charge flowing through a conductor, okay, per unit time, by formula. Okay, I can define it by formula: the quantity of charge flowing through a conductor per unit time. Okay, that is electric current. So we use the symbol I to represent electric current, and of course Q here is the quantity of charge and the T is time. Okay, and the SI unit of electric current is ampere, right, which by symbol is A. So please take note of that. Okay, the SI unit of electric current is ampere. Now I'm going to derive another formula of electric current. Now remember, okay, let's say you have a conductor, okay, let's say in terms a conductor, a wire, okay, that is actually cylindrical. A wire is just a tiny cylinder. Please take note of that. All right, that tiny cylinder. So it is actually having current flowing through it. Okay, there are current flowing through all the entire volume of this, okay, this current flowing through, and that current is the movement of electron from one part of the conductor to another. Now the current has velocity. Okay, so now first of all we're going to look at let's look at the velocity of the current. Okay, and of course in physics you know that velocity is given as length. Okay, displacement, which of course is length, displacement all over time, right? So now if I should make time the sort of formula here, remember I need to cross multiply. Okay, if I make time the sort of formula here, you should do that. Okay, the time should give you velocity all over, all right, velocity of all over length, because if that, no, as a mistake. Okay, the time should give me from this relationship, if I make it the formula, okay, the time should give me length divided by what? Velocity. Now this actually wire, okay, this wire actually is actually carrying electron. What is moving is electron, okay. So we simply mean that the charge that is flowing, this charge that is actually flowing is because of electron, because electron are charge carriers, okay. For example, one electron has a charge of 1.6 times 10 raised to the power of minus 19. All right. So the quantity of charge that is flowing through this conductor depend on the quantity of electron. Okay. So I can simply say that quantity of charge Q. Okay. And that way of expressing quantity of charge Q. Let me divide this. Okay. Is going to be equal to the number of electron. Okay. Number of electron. Okay. Multiply, because of course E is just one electronic charge. So to get the total number of electronic charge, I will use N. N is the number of electron, then times E, okay? Electronic charge, the charge of just one electron, okay? Let me just remove this minus, it's not necessary. And okay, then of course, depending on the volume of this conductor, I still need to multiply by the volume, okay? Because this conductor, the electronic charge, okay, will actually, the electron will fill up the volume of the conductor. So I need to multiply by the volume V. So let's capital letter V, right? So I want to rearrange this formula, right? So I have that Q is equal to the charge, quantity of charge is equal to the number of electron multiplied by E, the electronic charge, times the volume of the conductor. And we know that time from what we have here is equal to length, okay, all over velocity. Now, volume, please take note of this. Volume um, of course, in physics or in science, it's always given as area, okay, multiply by, of course, the height or displacement. So area times the length, okay, that is volume. Okay, so I'm going to put all this in now, all this T, both T, of course. From here now, I can simply Q is equal to, right, NE in place of volume. Okay, I have what, ALs, right? So I have this for time. Remember, current is Q, quantity of charge, divided by time, right? Okay, so now I have a relationship for this is for Q, my charge. Are you good? And this is for the time. So I have to replace everything now. For the charge, I put NE A times L. All right, then divided by, for the time, this is what I put, L all over V. Okay, of course, you know this is something as, okay, NEAL, then of course reciprocal times this will invert, okay, V, this small letter V, okay, velocity, let me differentiate it by just using small letter V, right? Small letter V. All right, then of course, then divided by, forget that this L. What I just did was reciprocal. I hope you know how to do that. Now this is the same thing as actually saying divided by L all over V. And when I change the division by multiplication, then the V comes, the velocity comes up, the L still remain on the denominator. So that's what happened here, and then divided by L. Okay, L cancels L. So that's another formula for current based on the velocity of the electron is given as the number of electron multiplied by electronic charge, then times the area of the conductor, then times the velocity of the conductor. So this is another way of expressing electronic charge. So please take note of that. So it's either you express electronic current, please, not electronic charge. It's either you express current as quantity of charge all over time, or you express the current passing through a conductor as the number of electron multiplied by electronic charge, the electronic charge, okay, multiplied by the area of the conductor times the velocity of the electron. So these are the two formulas. So you can just write that down. We will definitely apply it, okay. somewhere, right? So I'm going to actually proceed now. So the next thing I'm going to look at is what is known as resistance. Okay, resistance. Okay, so now remember, current flows through a conductor, and that conductor is always mostly metallic. Okay, and they are called electric conductors. Okay, so what is resistance? Resistance is defined. Resistance is the opposition. Is the opposition to the flow. Okay, so you can just specify, because there's a lot of resistance. So in this case, what you're looking at is electrical resistance. So you can just specify. So when someone asks what is resistance, okay, the question is gonna be what type of resistance? Is the electrical resistance? So electrical resistance is the opposition to the flow. Okay, position to the flow of electrical. Okay, position to the flow of electrical current. So take note of that. Okay, so that is why we have, okay, different materials, okay, based on their opposition. Okay, so electrical resistance is the opposition to the flow of electrical current. That is why we have, okay, electrical conductors. We have what is known as electrical conductors. Okay, because these electrical conductors, okay, actually allow the flows of electrical currents, but though there might be small opposition depending on the type of conductor. Okay, there might be small opposition. They will not have what is known as electrical insulators. Okay, for example, an electrical conductor is a metal. Okay, all metals are electrical conductors. Okay, why? Because they allow current to flow, and they offers low resistance to current. They offer low resistance to current. Okay, but if it is an insulator, okay, mostly these are non-metals, or of course non-metals, for example wood. Okay, or the metallic objects. All right, so this doesn't even allow current to flow through it. Okay, if you connect current through a wood, it can never flow through wood. Why? Because this material offers the current very high, okay, but high resistance, okay, up to infinite resistance. Okay, infinite resistance. That is why if you want to touch any wire that is actually naked, that has power, and you don't want to get electrocuted, you can wear a glove that is made up of insulator so that you don't get electrocuted. Okay, because of the resistance. So resistance is the opposition to the flow of electrical current. Now we are going to be interested in looking at the resistance of a wire. Okay, just a wire, right? Let's say a wire in form of a cylinder, as I told you. Okay, every wire is a tiny cylinder. That is tiny long cylinder, right? Okay, so now the resistance of a wire, of a conductor, okay, depends on the length of the conductor. So resistance is always given as this formula: resistivity multiplied by length divided by area. This is the formula for resistance. Okay, so this L here is the length of the conductor. L is length. So from this formula, we can simply say that as the length of the conductor increases, the resistance also increases, okay? Then of course, why the area A here is the cross-sectional area. Cross-section, okay? Cross-section area, excuse me. Cross-section area, okay, of this conductor. What I mean by cross-section is just the area of, just for this cylinder of this circle that this cylinder is actually made up of. And of course, the area of that circle is given as pi r square, right? So let's say we are considering this cylindrical wire, okay? And of course, the area of a circle is pi r square. And we also know that radius, this r here represents radius, right? Radius is diameter divided by 2, okay? So that's going to be pi, radius is diameter over 2, okay? Before you now square it. Okay, excuse me. Diameter divided by 2 before you square. So this is going to be equal to pi. If I square d, that will be d square. Then divided by, if I square 2, that gives me 4. Right, so that is the area, the formula for the area. All right. Okay, so now this is the next is this symbol. Okay, it's a constant for every material known as resistivity. Okay, every conductor has its resistivity, so that is why the resistance actually varies from one material to another. Okay, because of different resistivity. Okay, it's a constant depending on the zinc. If you are using zinc, zinc has its resistivity, copper has its resistivity. Okay, of course, so it's a constant. So this constant is resistivity. All right, so now what's the SI unit of resistivity? Let's see if we could actually make that, but don't forget the formula. Okay, so from what we have here, we can simply actually conclude that area is inversely proportional to resistance. Okay, the cross-sectional area is inversely proportional to resistance. All right, so let's look at we say that R is equal to resistivity multiplied by length all over area. So if I should cross multiply this, I have that resistivity, okay, is given by area times resistance, okay, then divided by length. The SI units of resistance is ohm. Please take notes, okay. SI unit of resistance is ohm. Then SI unit of area is meter square. Then divided by length. The SI unit of length is meter. So meter square divided by meter, I have just meter. So the SI unit of resistivity is ohm meter. Ohm, okay, meter. That's what that means. Okay, so I hope that is well understood. So please take note of this, okay. So let's look at a typical example where you have, okay, let's say you have a conductor, okay, a conductor, a cylindrical conductor whose radius is let's say 2 mm, and it's a conductor with resistivity of, let's say, 2 times 10, okay, raised to the power of 3. Okay, that's work for, okay, 2 times 10 raised to the power, let's say minus 6 ohm meter. And you are being asked to evaluate the resistance, okay, for the conductor of length, let's say 20 cm. Okay, so to get the resistance using that, that's gonna be equal to resistivity multiplied by length, okay, all over area. That's our formula, right? So that's gonna be, don't forget, 2 times 10 that's power minus 6, right? Then times the length, which of course 20 cm, we have to convert to meter. If you convert 20 centimeter, you have 0.2, that's the length. Then the area, okay, that's area pi d square all over 2, right? Pi is 3.14. Then the diameter, so I'm being given area, so I don't need diameter again, right? So I'm being given radius, please take note. To convert millimeter to a meter, okay, so that would be 0.002 all square. Okay, so let's do this. So this 2 times this gives me 0.4. Okay, then times 10 raised power minus 6. Okay, so let's go there. So I'm gonna use calculator to do this. 0.0, excuse me, I have 3.14, right, multiplied by, okay, 3.14 times 0.002 squared. What do I have? Okay, I have 0.0001226 000, okay, 126, right? Okay, so now let's now do the division. We can, so now 0.4 divided by 0.0000126, right? Okay, and of course 1 2 3 4 5. So if you do this, gonna give me this. What I have here is 31744 31746, then times 10 raised power minus 6. Okay, so this 1 minus 6, that will be 1 2 3 4 5 6. 1 2 3 4 5, right there 6. So if you do that, use your calculator, that's this something as this divided by 1 million, right? So divide that by 1 million, that's exactly what it means, because 10 raised power minus 6 is something as 1 over 10 raised power 6, okay? So you have to divide what you have here by 1 million, 1000, okay? 6 zeros, right? Okay, so of course 0.003, so the resistance here is 0.003 ohm. Okay, so I just use that to illustrate how you can calculate resistance using these parameters. Okay, so please take note of that as we look at the next subtopic. All right, so what do we have next subtopic? Okay, so we're going to look at electromotive force and potential difference. Okay, now you need to know the difference between electromotive force and potential difference. in as much as electricity is concerned. Electromotive force and potential difference. Okay, electromotive force EMF, right? Okay, so now please take note of this. This definition, okay, let me take this out, right? Okay, so let me make this definition very simple for you. Okay, now for before I actually give the definition, remember, before current flows in a conductor, there must be an energy, okay, that is actually supplied to it. And what provide that energy is mostly electric cell, okay? Okay, so let's electric cell is what provide that energy. Why? Because, okay, energy, all right, by an electric cell, if that is, can be energy by an electric cell can be in different form, but it is stored energy. All right. For example, if we are looking at electrochemical cell battery, we discover that this battery, let's say this is a battery, okay, this is a cell. This battery stores energy, okay, and it is, as it is here, it is not used. It's being stored. The energy is stored in form of chemical energy. Okay, it's stored in form of chemical energy. Okay, it is only when you now connect the conductor, okay, across this cell that is storing energy in form of a chemical energy, okay, this chemical energy now is now being converted to what? Electrical energy. So I want to give you the difference between, okay, EMF and potential difference. Okay, so first of all, the cell stores energy in form of EMF, okay, when it is not connected, and that EMF is in form of is chemical energy. Are you okay? Okay, so but it's measured in EMF volts. All right, so now once you connect it, all right, due to connecting it to an external conductor circuit, it will move current, it will flow current. It will now provide, once you connect it now provide potential difference. Okay, it's because it's only when you have potential difference that is when current flows. Okay, so now if I should, from this explanation now, okay, if I should say define EMF, okay, in a very simple term, I will simply say that EMF, okay, EMF, okay, electromotive force, of course. Okay, let me write that in electromotive force. Okay, is the energy stored, okay, which, okay, the energy stored, okay, a in a device, okay, okay, it can be a device, okay. I'll use source, right? Let's say that device can be in form of chemical battery in a device. Let's say battery, or it can be a dynamo. Okay, that's one way. It can be a dynamo because it can also be, what I mean by dynamo is a generator. Okay, dynamo, please. Dynamo. Okay, which provides the potential difference. The potential difference, right? for the movement, which provides potential difference for the movement of charge, okay, of charges in current current electricity. Okay, so this is one simple way of actually defining uh, electromotive force. Okay, it's a one simple way of defining electromotive force. All right. So one thing about science is you need to actually understand, of course, what you are defining. What you mean. You don't need to cram any textbook. Okay, definitely need to understand whatever you are defining. So electromotive force is the energy. Please take note. The energy. Okay, correct that energy stored in a device. Okay, can be battery, can be dynamo, which provide a potential difference for the movement of charge and current electricity. So which simply means that electromotive force is the stored energy. Okay, now how is electromotive force different from potential difference? Okay, so now it is not potential difference. Okay, that actually is the actual work. Okay, potential difference is now becomes what the work, okay, done, of course, in moving a charge, the work done in moving a charge. Okay, from one part of a conductor to another. So we simply means that if I have a conductor, okay, let's say from this part A to the part B, so the potential difference between these two parts, part A and part B, okay, this the two end is actually the work done in moving a charge, okay, from this part to this part. All right, and what provide the energy for that work to be done is EMF. So have you seen the difference now? So if you are being asked to differentiate between EMF and potential difference, so please take note of that. Okay, I hope that is well understood. Now let's look at EMF proper. Okay, how EMF actually supplies potential difference. I'm going to draw a simple circuit diagram. Okay, though there's another topic known as DC circuit, I'm going to draw a simple circuit diagram. Now let's look at a resistor to be, okay, or a load. Okay, please take note of that. A resistor, this is a symbol for resistor. Okay, let me call it R. Let's say it's a load, okay, that I need to supply current. Okay, let's say it's a conductor or whatever, I need to supply current. Okay, now that means I need to connect it across an EMF. Okay, so you discover that when I do this connection, current flows due to what this EMF provides, what potential difference. All right, but there are certain times I need to actually, okay, I want us to learn here. Okay, I think I have the note. Let's see if I should bring it up, if I have it here. Okay, it's called internal resistance of a cell. Okay, all right, let's bring it up. Let me take it up. Okay, so okay, here, so I'm going to be looking at something known as internal resistance of a cell. Okay, now the question is, what is the difference between cell and a battery? Okay, this is the symbol of a cell. It's just one cell. Okay, Battery is when you have is a combination of more than one cell. Okay, let's say this is just a cell. If you have just a cell, and of course, let's say the EMF is E. Okay, this is just one cell. But if you have a battery, there are it's made up of cells. Let's say you have two E1 and E2. Okay, and it is connected in series. All right, so that means the total. So for battery to get the total EMF is gonna be, you add them up. That's gonna be equal to E1, okay, plus E2. All right, depending on number of cell that it has. Okay, so this is a cell, while this is battery. All right, so now you discovered one thing about this. Okay, though it is not seen, every cell has its EMF. Okay, for example, if you go to the uh to go and buy normal tiger head cell, okay, you call that cell, it's called dry cell. Once you finish using it, you can throw it away. All right, its EMF is just 1.5 volts. All right, so if you need two of it to power your touch, okay, that means what you're having as the total EMF that you supply to your touch is going to be 1.5, okay, plus 1.5, which of course when you add that together will be totally what your supply is, what, 3 volts. Okay, so now, but there's one thing I notice, you should notice about cell. Even though some cell, their EMF they actually wrote on the body, they calibrate is 1.5, okay, but when you actually supply it, okay, to a load, it's not going to deliver this 1.5. Sometimes you discover that it will deliver something lower than 1.5. Okay, it can be deliver 1.3. Okay, you now ask what happened, why, what did, where did the 0.2 go to? Okay, now that is now what is bringing me to what is known as internal resistance. Okay, every cell, okay, mostly have internal resistance. They are not perfect. It's not an ideal cell. It doesn't deliver, it can't deliver all the voltage. Why can't it deliver the voltage? Because it has some internal opposition. Okay, of course, you know that very well. In mechanics, we have friction. Friction, okay, is actually opposition to the flow of opposition to motion, right? So the same thing with resistance, okay, is opposition to the flow of current. So internal resistance is gonna be the force opposition that this cell will have before it actually goes to the external circuit. Okay, so internal resistance, okay, this is the opposition to the flow of current in a cell. So this one happen is, that's why it's called internal. It happen in a cell. The flow to the flow of it, electric current in a cell. All right. So which simply means that if I want to draw the 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 symbol of a cell, okay, I will take note that beside the cell there's a small resistor that is not seen but is there, known as internal resistor. So I use small letter R to represent it. Okay. So before I can now connect this cell now to, okay, the external load, which of course is the external resistor, I use capital letter R to represent that. Okay, here we go. So which simply means that if current is flowing, current will flow both through the internal resistance to the external resistance. Okay, so current will pass through straight in a straight wire, okay, the same wire, through small letter R all over and big letter R. Okay, there's a man known as ohms. Now let's say this cell has EMF of E. Okay, now according to Ohm's law, you know that V is equal to IR. Okay, so in this case, the V is the supply, which of course is E. Okay, equal to I multiplied by R. So R I'm going to use for this circuit is not just this external R. That's another R, okay, in series. Both the R, external R, and the internal R, they are connected in series. Okay, and of course when resistors are connected in series, you add them. Okay, so that's going to be capital letter R, external resistance plus small letter R. Okay, so this formula is used, okay, for a cell that has internal resistance. Okay, so the EMF delivered by a cell is given by I, open brackets, small letter R plus capital letter R. Okay, so this can actually help if you want to get the current that that cell can deliver. Now the current that this cell can deliver is given by the EMF of the cell, of course, divided by when you make I the subject. Okay, big letter R plus small letter r. Okay, so please take note of this formula, right? So this formula we use in calculating current, okay, delivered by a cell that has internal resistance. Now, there's something I want to bring to your notice today. I want to expand this formula, expand it. I multiply the I by R. I'll have I capital letter R, okay? Then I multiply the I by small letter r. I have I small letter r. Okay, of course, this is the voltage. IR is voltage, okay? Now, let me use this. That means E now is going to be equal to, for I capital letter R, I use capital letter V. It's a voltage, right? Then for I small letter r, I use small letter V. Okay, so that means this E, the EMF will supply to voltage. The one that's supplied to the external resistor, okay, we call this voltage terminal voltage. Terminal voltage or terminal PD, okay? Terminal potential difference. Why this one that is used for the internal resistance, okay? Okay, that's used to overcome the internal resistance. That's what is known as lost volts. Okay, it is lost because it's based on, it's like friction, okay? So this is called lost volts. That means the EMF of a cell is going to be equal to the voltage, the potential difference across the external cell and the one that is lost due to internal resistance. Okay, so if you are being asked to define this, right? So let's look at now the definition of this two: lost volts and terminal PD. So let's start with terminal PD. Terminal PD. Terminal PD, of course, potential difference of a cell is the voltage or the potential difference okay across the external across the external load or resistance. Okay, that's the one that it delivers. Okay, it's the PD that it delivers across the external resistance. Okay, so please take note of this. While lost volts, okay, while lost volts okay, is the voltage or is the potential difference lost as a result of the internal resistance of the cell. So this is the difference. Okay, so that means every cell delivers to voltage, okay, to the external, which is terminal. Then the one it actually loses to, that it uses to overcome the its internal resistance, which of course is, this one is not made available, is lost. Okay, it's called lost volts. So please take note of that. Okay, so that's what we have here. I think with what we've gotten so far, we can look at question. Okay, so let's see if there's a question that we can work on. Okay, so I have an example here. So let's go there. So this goes like this. Okay, two cells, one One have an EMF of 2 volts and an internal resistance of 0.4, okay, and other having an EMF of the same 2 volts, right, an internal resistance of 0.1 are connected in parallel. So let's connect that. So there are two cells, two cells, they are connected in parallel. So I'll connect them with the internal resistance. So let's do that. So let's say this is the very first cell, okay, which the cell is said to be 2 volts, right? And of course the internal resistance then is connected in parallel with another, which of course is still 2 volts, okay, still having internal resistance, right? What's the internal resistance? Let's look at this, the internal resistance, okay. So okay, the internal resistance is 0.4 and of course the other one is 0.1, okay. So this 0.4 ohm and the other one internal resistance. Remember, internal resistance is always you just draw it beside in series with the cell, okay. So I've done that. Now let's continue with the question. They are connected in parallel, okay. The combination is then connected in series with a resistor of 5 ohm, okay. So after connecting the cell, the two cells, okay, are connected in parallel, then the combination now is now supplied to an external resistor, okay, according to the question is 5 ohm, okay. So what are we looking at? Let's start with draw the circuit diagram. I have done that, okay. So this is the circuit diagram. So this is I part of the question. All right, so I part of the question. Calculate the current through 5 ohm. So I'm looking for the current through this 5 ohm. So the current through this 5 ohm is the current that these two cells, okay, delivers to this 5 ohm. That is going to be the total current, okay. Don't forget the formula. Current delivered by a cell is given by the EMF of the cell, okay, all over capital letter R plus small letter r. I'll give you this formula, right? So it's going to be equal to, now the EMF of the cell, okay, is going to be, so the cells are connected in parallel to, they are 2 volts, okay. When cells are connected in parallel, you don't add up, the EMF is just, they are the same, you just one, okay. Just write the 2 volts. That's for parallel connection, okay. Then capital letter R, of course, we see is 5, right? Then of course we now have the small letter r. There are two internal resistance, 0.4 and 0.1, and they are parallel. So it's in, remember, in parallel connection, okay, for resistance we're still going to do this, okay. The total resistance when it is parallel is going to be 1 all over r1, okay, plus 1 over r2. There are two of them, okay. And of course I told you when we treated capacitors, once you have this, you can use a shortcut to get the total. Since they are just two, you apply product, okay, product of the two. That's how you get it, divided by the sum. That's a shortcut, right, to get the total resistance of two resistors connected in parallel. So that's going to be small letter r, and it's going to be the product. And of course two of them, one is 0.4, the other one is 0.1. So that's their product is going to be 0.4 times 0.1, right, and divided by their sum, 0.4 plus 0.1. Okay, so let's go there. So this is going to be 2 divided by 5 plus 0.4 multiplied by 0.1 will give me 0.04. Then all over 0.4 plus 0.1, that is 0.5. Okay, so let's get this over with. Okay, this is gonna be 0.04, right, divided by 0.5. Okay, so I have 0.08. So 5 plus 0.08, which of course is 2 divided by 5.08. Okay, so my current now is gonna be equal to 2 divided by 5.08. What do I have? So that would be 0.4 approximately. So the current, okay, delivered to the external resistor is 0.4 ampere. I hope that is well understood. Okay, I think that is it. Okay, is there another question we need to? Okay, so for now, that's it. Okay, we'll continue.